Welcome to ECE 3270, Introduction to PLC Programming, Lecture 9. So in this lecture, we're going to be going over an approach to programming and sort of a programming construct called state machines. State machines are a powerful way of approaching a programming problem, and we're going to see a couple of example applications worked out. That being said, this should connect in your mind to what we've talked about previously about maintainability and readability. So programming code that is not maintainable and not readable, which readable has implications for maintainability. If it's not readable code, it's probably not maintainable code. So programming code that's not overall maintainable is mostly a waste of time. So we always want to make sure that the code we write is readable and maintainable. And as we've talked about previously, readability and maintainability relies on that it has a logical structure. It's part of writing code that is readable and maintainable. And we've talked about a couple of different ways of structuring code so far. Number one is logical groupings of rungs and using comments. And that's a very good way of going about it. And there's also techniques that we have developed and shown, such as the bit latch sequence, right? So that's one way of approaching a problem that has a specific order is by using a bit latch sequence. And that imposes further order on the specific shape and formation of each rung, right? There's a previous step, not this step, whatever conditions you have, and then the latch for the current step. And that's true for every single step in the bit latch sequence. And so it allows a structured approach to the problem. Well, so this is yet another structured approach to a problem, but it solves a bit of a different problem. It's not such a situation where we have a certain specific order as it is events and consequences of events. So what happens when a certain switch comes on given the certain status of the machine? What happens when the user opens the door when the machine is in motion? So given the current state and an action or event, what state does the machine need to go to next? So it's a different way of thinking about and approaching a problem, and it's one that we're going to apply and see how we can use when programming PLCs. But first, let's have a quick industry connection video. So in this video, first of all, this does connect with state machines as well as what is listed here as LVDTs. But there's two different points I want to make. So first of all, in this industry connections video, we're going to see LVDTs used to measure something very precisely. So LVDT stands for linear voltage distance transducer. So it is going to perform a linear translation from distance into voltage. So given some distance, there's a linear relationship between the distance and the voltage output by this sensor. So this is just a very practical way of measuring something. If two things are a certain distance apart, that distance is directly proportional in a linear fashion to the voltage output by the sensor. So there we go. It's a distance sensor. That's what an LVDT is, a very precise distance sensor. So we're going to use these distance sensors to measure the precise thickness of shims. We've talked about shims in the past. We talked about them in the lab where you had to do some things for a company called Transmission Makers of America. So they were using shims in their transmissions, and they needed to be a certain size. Well, this is how you would verify that the shim which was picked from the bin actually did match the size that you needed. You would take the shim, place it into a gauge, and then measure it with some LVDT. And if it was in the tolerance range, you'd put it into the transmission. And this machine does something very similar. So this is introducing how more precise sensing can be done in industrial machinery. And it also introduces a complex set of behaviors. What we're about to see is this robot pick up a part, load it to this nest, and then the next thing that it's supposed to do is get a shim, verify that it's the right size, and place the shim to the nest. But we're going to see the robot cycle through several shims until it gets one that actually does match the appropriate range when it is measured. So this is a demonstration of how a state machine works. The state the machine is in when the robot is trying to get the shim of appropriate size is the pick shim state. And so the robot is cycling through, picking a shim, and then it wants to move on to the next state, which is place shim at nest. But the problem is it's not getting the shim matches correct size signal. So the state of the machine is pick shim, and it can't move on to the next state, which is place shim, because the signal keeps saying this is a bad shim. And so we're stuck looping back into the state we are currently in. And it's actually a little bit comical, so let's see this video. So here it grabs the first part, places it to the nest. And here we go. Is this shim the right one? It says no. Put it back. And see, the thing is, you'll see it always grab from the second bin because that's the correct bin that it should be picking from. The issue is this bin has been filled with the wrong size shims. So when it measures outside the correct range. It puts it back. How about this one? Nope. So we're stuck on this state. We keep looping back to the same state until finally we're going to find a shim that is the appropriate size, and we'll get the signal and be able to move on to the next state. Not yet. There it is. So we finally got the signal and we moved on to the next state, which was place shim at nest. And now we're moving on to further states. So notice, you might be thinking, well, why couldn't we use a bit latch sequence for that? Well, you could, potentially, but it's not actually a great fit because it's not a simple progression of here's the order of operations, 1, 2, 3, 4. It's we want to pick shim and we want to place shim. But the only way to go from pick to place is if we get the signal shim correct. So we keep getting a different signal, which is shim not correct. And so instead of being able to just move through this one step to the next step in just a linear fashion, what we have instead is this situation where we're stuck in this state and we're trying to pick a shim that is the appropriate size, and when we get the signal saying it's not the appropriate size, we loop back on ourselves, pick another shim, measure it. Is it the appropriate size? No, no, no. And we'll stay here forever until we get the signal that we have finally picked a shim of the appropriate size, and we move on to the next state. So see the difference. We're not just going through a linear sequence of events, pick shim, place shim, and so forth. That's not it at all. We're going pick shim, and if the shim's right, we'll place it, but if it's not right, we're going to pick again. and it's not right, so we pick it again, and it's not right, so we pick it again. So this is a state-driven situation, not a simple linear situation. So it's sort of like a hammer and a screwdriver. You have different tools in a programming toolbox, different approaches to solving a problem. When you have a linear sequence of events that you need to happen in that specific order, this is the bit latch sequence is a great way to go about it. But when you have a set of things that need to be done, but it's based on the state and environmental conditions, then a state machine is a better approach. So with that being said, we're going to dive into how state machines work and how to approach programming them. So we've talked a little bit about the importance of having structure in a program and how that facilitates maintainability and also allows to actually have substantial complexity in the program and achieve functionality in a substantially complex environment. So now we're going to turn our focus toward learning one of these specific structures, the state machine. All right, so first of all, the state machine was developed in Bell Labs independently by two guys named George Mealy and Edward Moore. So Bell Lab, first of all, if you haven't been exposed to much about Bell Labs, is a fantastically interesting read. If you ever have time, just explore the Wikipedia page on Bell Labs. The short version is it was founded by Alexander Graham Bell when he invented the telephone. They are responsible for many of the modern things that we have today, such as the transistor, laser, the entire modern idea of information theory. Claude Shannon invented while working at Bell Labs and was a contemporary of George Mealy and Edward Moore, who created state machines. The Unix operating system was invented there, C++, solar cells, CCDs, so charge-coupled devices. CCDs are the chips in a camera, in a digital camera that allows you to image. And interestingly, the Carnot map. So if you've had digital systems, then you probably have had to learn to use Carnot maps. So also developed at Bell Labs. So a very, very interesting time in history for engineering. Okay, so back to state machines. So let's take a small example of just a simple sort of toy problem to understand exactly what a state machine is. When we define a state machine, there's a pretty well standardized process that I'm going to show you to go through. So first of all, we have to specify the function in plain English. So here's where we're going to put that. So plain English. All right, what we want this state machine to do is we want to have two states, S1 and S2, and when you're in state 1 and you get the input T, we're going to transition to S2, and when you're in S2 and you get the input T, we're going to transition back to S1. When you're in S1, you'll give output S1. It's a Boolean output to designate that you're currently in S1. When you're in S2, you will give a Boolean output called S2, designating that you're currently in S2. So putting that in words, if in S1 and T occurs, transition to S2. If in S2 and T occurs, transition to S1. While in S1, output S1 should be on. While in S2, output S2 should be on. Let's see, is that it? So we're in S1, T occurs, we transition to S2. When we're in S2, T occurs, we transition to S1. When you're in S1, S1 is on. When you're in S2, S2 is on. It looks good to me. So here's why it's important to first of all start out by, in plain English, stating what you want the machine to do. If you're not able to clearly explain what the machine is supposed to do, how are you possibly going to program it to accomplish that task when you can't even put it in plain English? So by putting it in plain English, it allows you to fully understand what it is you intend it to do. So we've written it in plain English. This is step 1. Now, the next step is to define each of our states, inputs, and outputs. So, states, we will have state S1, and we'll also have state S2. All right, inputs. Well, we said that the only input we're going to have is, right, T for transition, so T. I used a uppercase up over there and a lowercase over there, so we'll make that hybrid. All right, so we've got our inputs, T. Outputs. Outputs are actually the same as our states, right? We're going to have an output S1, which is a Boolean, and an output S2, which is also a Boolean. All right, we have now completed step 2 to defining a state machine. State 3, draw the diagram. This is what a state transition diagram usually looks like. You'll have your states represented in circles. So we've got S1 and S2. Transitions are shown by arcing arrows. And then what causes that transition typically goes on that transition. So for instance here, if we're in S1 and we receive the input T, then we transition to S2. If we're in S2 and we receive the input T, then we're going to transition to S1. That just leaves outputs, which do not typically get represented on the state transition diagram. So step 3 is complete. State transition diagram. Next, we have to actually choose how we're going to encode what state we're in. So remember, like I said, when this was created by Mealy and Moore, it was envisioned that this would actually be a physical circuit, right? But in a PLC, we're not going to actually build the circuit, right? We are just virtually approximating that circuit. So we have to choose how to encode our current state. But remember how we have to have it work, right? We can only be in one state at a time, and we can only be in the available states. So in this case, S1 and S2. Well, the easiest way to go about that, to actually make sure that you can only be in one state at a time and that you can only take on certain values, is to develop our own UDT. But that's a bridge, I think, a little too far. It's unnecessary. So rather than doing that, what we're going to do is we're going to define a tag that is an integer. So, right, we're going to have a tag called state, and it's an int, and S1 is going to be equal to the number 1. Creative. S2 is going to be equal to the number 2. So we have some integer tag named state, which will take on the value 1 when the state machine is in S1, and will take on the value 2 when the state machine is in S2. There we go. So that is step 4. Choosing the state representation, how we're going to encode it. All right, the last thing that we would actually have to do is to program this. That's the last step. Once you have fully defined the functionality in plain English, you have written down all the states, inputs and outputs, drawn the state transition diagram, and chosen an encoding for the state, all that's left to do is program it. And it's done. So we've got a comparison to see if we're in state 1, right here. If transition T occurs while we're in state 1, we will move 2 into our state. And then we'll be in state 2, right? And while we're in state 1, while the state is equal to 1, S1, the Boolean tag S1, is on because of this OTE. And when we're not in state 1, right, this EQU will not be true. So then this S1 OTE will be off. And the same logic applies down here. So if your state is equal to 2, then when T occurs, you will move a 1 into state, and you'll become in state 1. And similarly as to above, while you're in state 2, S2, the Boolean tag, will be on due to the OTE. So we have successfully described what the machine was going to do. We have written down all the states, inputs, and outputs. We have drawn the state transition diagram, and we have chosen an encoding for the state. And finally, we have actually drawn the ladder diagram that will run it. So we have written out the code. So we have completely defined this state machine. So our first example of a state machine was fairly simple. And to be honest, it was a little bit contrived, right? So we were just arbitrarily going from state 1 to state 2 and toggling back and forth. So state machines really exemplify their impact and power when you see how well you can capture everyday devices that you could want to program, how well these state machines can capture their functionality. So as an example now, what we're going to move to is doing a lock. So imagine that this is the case where we have some sort of electronic locking system. We will still keep it simple in the functionality of the lock, but we're going to approximate that functionality. So, number 1, we have to describe it in plain English. So, it's to remain locked, right? If we're already locked, we want to remain locked until the correct key is inserted. When the correct key is inserted, then unlock. When the key is removed, lock back. Okay, there's our plain English description. So we'll mark that by step 1. Step 2, we have to define the states, inputs and outputs. So our states, well, we've got locked and we've got unlocked. Inputs. Well, we've got correct key present, and that's it. Because we don't actually need another input. We just need to know if the correct key is not present. So it's a Boolean variable. Either it's there or it's not there, right? We either have the correct key or we do not have the correct key. If we have the correct key, unlock. If we don't have the correct key, lock. Correct key present. Outputs. We didn't actually define any outputs in our plain English description, right? But what we did say was we want to unlock and lock. So actually that does require some sort of interface with the outside world. If the correct key is present, we should open the shackle. The shackle is the metal part of the lock that goes up and through whatever it is you're locking, right? So If we want to unlock, we're going to open the shackle. When we want to lock, we're going to close the shackle. So that's our outputs. Open shackle and close shackle. Step 2 done. All right, step 3, drawing the state transition diagram. Well, actually it looks fairly similar to our S1 and S2. We have lock and we have unlock. And we have a transition from lock to unlock, and we have one from unlock back to lock. How do we transition to unlock if we're in the state locked? Well, correct key present. Equals true. And to go from unlocked back to locked, all we have to have is correct key present equals false. One extra notation we're going to add here is that if we are unlocked and the correct key is still present, we are going to remain unlocked. So correct key present equals true. While we're already unlocked, then remain unlocked, right? And similarly, if we're already locked and the correct key is not present, then remain locked. So that's a common thing in state machines that you'll see, is you don't just see transitions away from the current state, you'll see transitions back to the state that you're already in situations where an input could potentially cause a transition or an input is changed. So, for instance, this is a situation I can imagine happening. Someone has inserted an incorrect key, so the lock is locked, right? It's in the state locked, L. They take that key out, so technically the inputs have changed, but we go back to locked. And then they try another wrong key, and we again go back to locked. But then they enter the correct key and it transitions to unlocked. So, just a notational thing. And that's step 3. Finally, we're going to choose a state encoding. We're going to stick with integers. So, state encoding int. So 1 equals unlocked, and we'll go with 0 for locked. And that was step 3, or 4. Now the only thing left to do is program it. So on the right you'll see our 2 rails, the left rail being the positive rail and the right rail being the negative rail, that you usually see in a ladder editor. So at the top we're going to have our state transition logic. So before you ever worry about outputs, worry about controlling the state transitions. First of all, if the correct key is present, then we're going to move a 1 into our state. So we'll use the MOV move instruction. We'll move 1 into the integer state. Okay, so when the correct key is inserted, we move a 1 into the state. Good, we're good to go. All right. If the correct key is not present, we'll shorten present to pres, then we're going to move a 0 in so that the state machine goes into a locked state. So again, using the MOV command, we'll move a 0 into the state. So fairly simple, right? If the right key is in the lock, we move a 1 into the state. 1 means unlocked. If the correct key is not present, we move a 0 into the state. 0 means locked. So that's our entire state transition logic. It's pretty simple. So we're going to put a dashed line here showing that we're separating our transition logic from our output logic. And over here we're going to write transition. Now, what are the outputs? If we're locked, and how do we tell if we're locked? How do we tell if we're in state 0? Well, we use an EQU command, right? And equals. So we're going to check and see if our state is equal to 0. So if the state is equal to 0, we're going to close the shackle. And if the state is EQU to 1, then we're going to open the shackle. And that is our output logic. So in this state machine, we have captured the basic functionality of a key lock that we're apparently going to implement digitally in a PLC. And it has two states, right? It has a locked state, it has an unlocked state. The state is controlled by the presence of the key, and there's some sensor to be able to detect if the right key is present. If it is present, then we transition from locked to unlocked. And if the key is removed or a incorrect key somehow magically appears in the lock, then we're going to transition from unlocked back to locked. If we're locked and the correct key remains not present, we're going to stay locked. And if we're unlocked and the correct key remains present, we're going to stay unlocked. And we have coded that into our ladder logic. There's our state machine. It would be easy then to have this running in a PLC and it actually function. Okay, so we're going to work one more example. This is going to be an elevator, but it's going to be a simple elevator. Otherwise, we wouldn't be able to fit the ladder logic onto the screen. So step 1, define in plain English what this thing's going to do. What is a 2-floor elevator? Okay, well, a 2-floor elevator is an elevator that, well, obviously services 2 floors. There's a button, right, to call the elevator at each of the landings where you can get on. Then there's also buttons inside the elevator to tell it that you want to go to the other floor. There has to be a floor 1 and floor 2 inside the elevator because you don't know what floor they're going to get in on, and you don't know what floor they're going to want to go to. The buttons on the outside of the elevator, those on the landings that call the elevator, are going to function the exact same as the buttons inside the elevator. So what I'm saying here is, if I'm on floor 1 and I push the button saying that I want the elevator to come to floor 1 to pick me up, that will function the same as being in floor 2, getting in the elevator, and pushing floor 1 inside the elevator. In both cases, the elevator is going to move to floor 1 and open the door. So functionally, those buttons are going to be considered to be the same input, which is call to floor 1. And then the call to floor 2 inside the elevator and outside the elevator will be considered the same. That's basically it, right? So the elevator is going to, when it receives a call to floor 1 and it is on floor 2, the elevator will first close the door because the elevator can't move with the door open. So the elevator will first close the door, then we'll go to floor 1 until, well, more precisely, it will go down until the input present at F1 comes on, at which time the door opens and the functionality has been completed, at least for that call. calling to floor 2 would be the same, right? Someone's at floor 2, they push the button. The elevator is at floor 1, presumably. Before the elevator is allowed to move, the door will close. Then, once the door is closed, the elevator will go up until the present at F2 input comes on, at which time it stops going up. Then it will open the door, and that has completed the functionality for the call to floor 2. Okay, step 2. Let's enumerate the states, inputs, and outputs. Okay, first of all, states. We have taken a bit of a jump in complexity from our toy problem to our lock and now to our elevator. So naively, we can obviously see that we're going to have an at floor 1 and at floor 2 state. However, it's not really enough, because there is a certain period of time where the elevator is transitioning from floor 1 to floor 2 or from floor 2 to floor 1. So we really need to have a unique state for when the elevator is going to floor 1, because that is not the same as being at floor 1, right? So we're gonna say going to floor 1. And going to floor 2. And that'll do it. Keep in mind, there's multiple ways that you could define a state machine to capture this functionality. There's not just one. But this is one way to go about it. All right, so what are our inputs in this situation? So we alluded to several of them. So number one, we didn't say this explicitly, but it's pretty important, right? We said that the elevator is not allowed to move unless the door is closed. So we have to have door closed. It's a pretty important one. We have to have our buttons, right? The buttons at the landing that are also the same functionally as the buttons inside the elevator. So call to floor 1 and call to floor 2. And then lastly, so the way that the elevator works is it'll be at floor 1, someone presses call to floor 2, and then it goes to state going to floor 2, right? And now the elevator is going up. And it'll stop going up when it gets a present at F2. So we have to have our present at floor sensors. So we're going to have a present, and we'll just abbreviate pres at F1 and pres at F2. There we go. There's our inputs. All right, now outputs. So we didn't explicitly state any outputs in our description, but if we think about how it's going to have to interface, how our state machine is going to have to interface with the real world around it, then it becomes pretty clear. What is it actually going to have to manipulate? Well, okay, it's got to open and close the door, and more importantly, the more important function of an elevator is that it goes up and down. So let's just start there. So we've got outputs. Door open and door close. Then we're going to have move up, and we're going to have move down. Okay. Not bad. Step 3. State transition diagram. Okay, so we're going to have an at floor 1. We will have an at floor 2. And we're going to have a going to floor 1 and a going to floor 2. and going to floor 2. Perfect. Okay, now let's draw our transitions. So, first of all, think about this. In the way that we define this, we said when a call to floor button is pressed and the elevator is not already at the appropriate floor. So, there's a possibility, there's a situation here where we're already at floor 1 and someone walks up and they're not really paying attention, right? And they press call to floor 1, in which case we're just going to stay right where we are. So that's a situation, again, where we're going to have a self-transition, right? So if we're at floor 1, so we're in the state at floor 1, and someone presses call to F1, well, we just stay where we are. And we're obviously abbreviating the input call to floor 1 as call to F1. Similarly, over here, if we're already at F2 and somebody walks up and presses call to F2, well, we just stay where we are. So call to F2. All right, simple enough. Okay. So, but what if someone walks up and presses call to floor 2 when we are at floor 1? Well, then we're going to have a transition from at floor 1 to going to floor 2. All right, and that's going to happen if someone presses call to F2. Similarly, if we're at floor 2 and someone walks up at floor 1 and presses call to floor 1, then we're going to transition to going to floor 1. Again, also triggered by call to F1. All right, so if we are going to floor 1, if we're in state going to floor 1, we're going to have to eventually get there, and we'll transition to at floor 1. But we will transition when the present sensor comes on at floor 1, right? So we're in the transition. Someone walked up to the elevator, they got in at floor 2, they pressed call to floor 1, and the elevator starts moving down. Well, it's going to stop and say I'm at floor 1 when present at F1 comes on. So the exact same thing obviously is true over here. Someone walks up when the elevator is at floor 1, they get in, and they press go to floor 2, or call to floor 2 is the correct terminology. Then the elevator is going to move up until present at F2 comes on, at which time it will the state machine transitions from going to floor 2 to being at floor 2. So there we have it. We have a state machine that fully represents the situation. And we will once again use an integer to encode our state. So state encoding, we're going to choose int. What a surprise, right? So now let's enumerate our states. Okay, so look up here at our state transition diagram. We've got 1 state, 2, 3, 4. You probably already noticed this, and this is probably extremely obvious, but for each state in our state transition diagram, we have to have a state encoding. So we're going to have at floor 1, we're going to have going to floor 1, we're going to have at floor 2, and we're going to have going to floor 2. So each of these will be equal to some integer value, which we're going to define. So let's say that at floor 1 is equal to 0, going to floor 1 is equal to 1, at floor 2 is equal to 2, and going to floor 2 is equal to 3. Okay, now let's program it. In the interest of time, I'm going to quickly draw the transition logic on the left and the output logic on the right. Okay, so let's discuss the logic. First of all, at the top on the left, in our state transition logic, if we are currently in state 0, which means we are at floor 1, and we receive a call to floor 1, so we're at floor 1 and we receive the input call to floor 1, then we transition again back to state 0, and that's all that we have to do according to our state transition model. If we are in state 1 and we receive a call to floor 2, then we are to transition to the state going to floor 2, which is represented by the number 3. So we receive a call to floor 2 and we move a 3 into our state. Now, let's say that we are going to floor 1, so which that means we are in state 1, and then suddenly we get the present at floor 1 sensor. Well, then we are to move a 0 into the state representation. The logic for floor 2 is very similar. If we are currently in state number 2, which state number 2 means we are at floor 2, so right here in our logic, and we receive a call to floor 2, then we don't do anything, right? We just again move 2 into the state. If, however, we're at floor 2, so we're in state 2, and we receive a call to floor 1, we are going to move a 1 into the state encoding. So moving a 1 into the state encoding means we're going to the state going to floor 1. All right. If we were going to floor 2, which means we were in state 3, and we receive a present at floor 2, then we are going to move a 2 into the state. So again, unpacking that, if we're on the way to floor 2 and suddenly the sensor that means we are at floor 2 comes on, then we are going to change states. We're going to transition from going to floor 2 to being at floor 2. So that's our state transition logic. Now, the way that you code this, you write the state transition logic absent from worrying about your outputs. Once your state transition logic is right, then worry about your outputs, okay? So now we move to the output side. If we are in state 1 or state 3, so we'll go over here and look in our state encoding, right, over here, and state 1 and 3 are going to floor 1 or going to floor 2. So if we're going to floor 1 or going to floor 2, then the door has to be closed. Very important. Got to make sure the door is closed if we're going to a floor. All right. However, if we are in state 0 or state 2, and again, going and looking at our encoding table, 0 and 2 are at floor 1 or at floor 2, then our door should be open, right? Because people are going to want to get in or get off the elevator. Simple. Makes perfect sense. We've used OTEs, and I think that works out fine. So these are Booleans that are controlling the door. Okay, if we're in state 1, again, state 1, going back to our encoding table, is going to floor 1. So if we are going to floor 1, and, so logic here is an and, right? And the door is closed, and, another and, we are not currently present at floor 1. So we're going to floor 1, our door is closed, and we're not at floor 1 yet, then move down. Okay. So all that says is if you're in the state that is going to floor 1 and the door's not closed and you're not currently at floor 1, then you have to move in the downward direction. And we have conditioned it on the door being closed. That makes sense. You don't want to move if your door's not closed. And we have included that we're not already at the floor. Yeah, if we're at floor 1 and someone, presses the button and for whatever reason it flips to state 1 for a half second, we don't want to move down. We're already at floor 1. So that works. And we've duplicated the logic to work for going up to floor 2. So if we are in the state which is going up to floor 2, going to floor 2, and the door is closed, and we're not already at floor 2, then move up. So, someone gets in the elevator at floor 1, and they press the button to go to floor 2, call to floor 2, right? the door will close, at which point the elevator will begin to move up. And then it will stop going up and will change states to being at floor 2 because of the state transition logic when it reaches floor 2 and the sensor comes on. So there we have it. We have successfully coded our elevator state machine. So in summation, we discussed the importance of structure. We discussed state machines. Their history. What they are. And how to use them. As far as how to use them goes, what you need to remember is the more or less 5-step process that I showed. So 1, describe it in plain English. 2, enumerate the states, inputs, and outputs. 3, draw the diagram. 4, choose a state encoding. 5, program it. So, that's what we've covered. Please make sure that you understand this. It'll be very helpful to you if you ever are in a professional PLC programming environment. Beyond that, it is necessary for the lab this week and next week. If you have any questions, please feel free to email